Hello, my name is Bahman Abbasi. I hold the Bachelor of Science in Geology, a Master of Science in Geophysics, and a PhD in Environmental Science from University of Quebec. Currently, I'm a postdoctoral researcher in mining engineering at the University of Quebec. My work focuses on developing advanced uh, tools for geophysical data interpretation, specifically targeting mineral deposits. This study introduces new methodologies for 3D integrated interpretation of multiple geophysical images, focusing on epithermal gold exploration. Traditional borehole data interpolation lacks spatial information in areas where borehole coverage. Consequently, these methods cannot introduce new geological insights where borehole data is absent. This example shows that the false horizontal layering inferred from the lack of borehole data at the margins makes a problem in interpretations. When interpolating borehole data, the uneven distribution of boreholes creates gaps, making interpolation challenging. However, geological formations respond differently to geophysical measurements, presenting significant challenges in analysis, particularly when alteration and mineralization overlap with the background geology, distorting the measured signals. The sensitivity of the various geophysical methods to different geological patterns, and the fact that multiple patterns may be reflected in the measurements complicates the interpretation. Key questions to address are how can we accurately estimate the physical properties from complex and overlapping geophysical signals? How can we separate hidden geological patterns? And finally, how can we integrate the extracted patterns to reconstruct a robust geological model supervised with limited borehole information? Initially, we have access to two main sources of information: known geological data and multiple geophysical datasets. Geological data, typically in the form of borehole data, is often incomplete, sparse, and expensive to acquire. In contrast, geophysical surveys provide a comprehensive, regular, and cost-effective means to calculate 3D physical properties, making them a valuable alternative. These 3D physical property models can be refined using known geological data and other reliable geophysical interpretations, addressing the first question. The second question is tackled through 3D feature extraction, where our numerical tool separates overlapping geological sources within geophysical property images. And lastly, feature selection addresses the last question. A 3D spectral learning algorithm supervised by existing borehole geological information predicts and reconstructs geological targets. This bedrock geology map of the test region is compiled from borehole samples. The oldest rocks are layered volcanosedimentary units intruded by felsic to intermediate porphyritic intrusions, with the younger dioritic intrusions to the northwest. We developed 3D lithology models based on drill core datasets. The cross-section of the 3D model is shown here. Gold enrichment are observed from shallow to depth down to 600 meters, primarily within felsic volcanic rocks. This horizontal slice of the 3D susceptibility model shows borehole sample susceptibility readings for comparison with bedrock geology. In both plan view and cross-section, most magnetic rocks are mafic volcanic rocks and dioritic intrusions, with felsic volcanic rocks and porphyritic intrusions display the lowest magnetic susceptibilities. Gold enrichment is associated with this low susceptibilities in felsic volcanic rocks. The observed geophysical anomalies include magnetic total field intensities, DC resistivities, and induced polarization chargeabilities at deposit scale. This slide presents preliminary 3D inversion results of DC IP data at the prospect scale. The recovered chargeabilities also show a correlation with susceptibilities. Felsic to intermediate porphyritic intrusions and felsic volcanic rocks exhibit low chargeabilities and susceptibilities, whereas mafic volcanic rocks and dioritic intrusions display high chargeabilities and susceptibilities. This relationship indicates that IP chargeabilities can be used to constrain the magnetic inversion. Nevertheless, this relationship is not perfectly linear. This necessitates careful isolation of certain areas in the 3D inversion of magnetic data from DC IP influence. The IP model's magnetic response is similar to the measured magnetic response, but discrepancies exist in some areas. We aim to focus we aim to use DC IP information in magnetic inversion only where a clear link exists between them. In areas with greater similarity, DC IP can influence magnetic susceptibilities. Where similarities are fewer, inversion relies on observed total field intensities. We developed a non-uniform weighting model by multiplying the standardized maps, which scale from 0 to 1, with low weights indicating less influence from DC IP inversion and high weights indicating more influence. Here are the results of the non-uniform inversion. As shown, the global weighting W equal to 0.01 produces a more realistic susceptibility model, accurately mapping both high susceptibilities of mafic volcanic rocks and diorites, as well as low susceptibilities of felsic volcanic rocks and porphyritic intrusions. 4 petrophysical domains are identified through cross-correlation of physical properties. In this study, we utilized this refined 3D integrated model to extract 3D patterns for geological interpretations. One critical requirement in 3D predictive modeling of geological patterns within multiple geophysical 3D images is the accuracy of depth estimation of the physical property sources. The 3D cooperative inversion strategy enabled us to refine more reliable 3D physical property models before applying feature extraction and machine learning algorithms. Without this level of accuracy in 3D physical property modeling, the output of the machine learning predictions would likely be erroneous regardless of the method used. We propose here a 3D hybrid system called 3D spectral feature subset selection. Here is a screenshot of the software we developed for 3D feature extraction and selection. The tool performs several dimensionality increases and reductions to extract and select features related to specific geological patterns. Like the previous slides, multiple 3D inversions provide 3D physical properties. Then independent component analysis, ICA, is used to extract independent components. That is called a spatial feature extraction. And then a continuous wavelet transform, CWT, decomposes these 3D components into raw spectral features, further separating overlapping features. ICA is then used to isolate frequency-dependent features producing independent spectral features for machine learning. This is called spectral feature extraction. The spectral feature subset selection algorithm is based on multi-layer perceptron neural networks, optimizes output using a by objective genetic algorithm. This method selects the most relevant input features, avoiding irrelevant ones that can mislead predictions. Throughout the feature selection process, several phases of dimensionality increase and reduction occur, ultimately linking independent patterns to geological targets by feature subset selection. Compared to conventional machine learning approaches, our method can automatically detect redundancy in the inputs, which ultimately increases the accuracy of the predictions. For comparison, a conventional machine learning algorithm with 4 submodules was employed. Pre-processing prepares the datasets using 3D inversion, interpolation, and filtering methods. Spatial feature extraction with NICA or negentropy maximization ICA, independent component analysis. Separates the image overlaps in 3D. And then spectral feature extraction with CWT NICA, continuous wavelet transform negentropy maximization ICA, extracts the wavelet decomposed features. Further, the machine learning algorithm with MLP adjusts network weights W1 and W2 to learn patterns inside the extracted features based on the sample targets. However, our proposed approach is called spectral feature subset selection. The algorithm follows similar steps: pre-processing, spatial feature extraction, spectral feature extraction. However, the machine learning component is formulated as a bi-objective optimization problem. The algorithm minimizes the bi-objective function f while adjusting the network weights W1 and W2 and simultaneously selecting the relevant combinations of extracted features. S represents selected features, while the red R's denote redundant features. Physical property models are derived from cooperative inversion of magnetic and DCIP datasets. A preliminary fast ICA separates latent features within the physical property images, with results shown here as 3 negentropy maximized independent components. We decompose 3 independent components into raw spectral features using continuous wavelet transform. We calculated the wavelet coefficients for 3 scales and in 72 directions on 3 images. This results in 648 3D raw spectral features, presented here on the plan view. The dimensionality of the raw spectral features is then reduced to 227 independent spectral features with ICA. The extracted independent spectral features are compared to the limited geological target, for example, the gold concentrations here. Through a genetic algorithm, the neural network learns to predict gold concentrations based on the extracted features. 70% of the targets are used for training and 20% are kept randomly for training validation to avoid overfitting, and 10% of the non-information is reserved for testing. The proposed method consistently outperforms the conventional method in gold predictions, with higher R-squared values during both validation and test phases. This indicates that the proposed model is better at generalizing to new data and capturing the underlying patterns in the datasets. The error landscape shows that the best results are achieved in the last generation, with a maximum of 209 selected features presented as the last global error indicated by the dark blue color. The feature extraction process identified 18 spectral features as extremely redundant in predicting gold concentrations. As can be seen, the proposed algorithm effectively recovers a 3D gold grade model from 3D geophysical images. Using a similar approach, the algorithm was also successfully trained with the borehole lithotypes to predict lithological models. Again, the best results are achieved in the last generation with a maximum of 200 selected features here. The feature extraction process identified 18 spectral features as extremely redundant in predicting lithotypes. As can be seen, the spectral feature subset selection method reconstructed a more consistent lithological model compared to traditional interpolation methods and conventional neural networks. The diuretic intrusion is clearly mapped in red, mafic rocks in green, and felsic rocks which host gold mineralization are represented in blue. Thank you.